Let me introduce you to Nico, our next speaker, who is with SureChem, and he is the managing director. For 11 years, Nico has been in text and data mining software, and for the last 5 years, he's focused on chemical information. So Nico says that there is a revolution taking place in chemistry and access to data. This results in change in technology, business models, and user attitudes. How are Chemexon and SureChem contributing to it? Let's find out. Over to you.
Hi. Okay, everybody can hear me okay? Yeah, some of you probably think that all I ever do is really hang around Chemaxon meetings. But they're fun, and you learn a lot. Anyway, so I'm going to talk today about some benchmarking that we've done with Chemaxon's new name-to-structure tool. And I gave a presentation similar to this in Budapest in June. And it was reasonably well received. Everybody seems quite fascinated with name-to-structure benchmarking, which just goes to show how far I've gone from my dreams in college of becoming a diplomat. That I'm interested in this too. So that talk, we decided to do it here for the U.S. audience. But since then, Daniel and Rita and the rest of the Chemaxon team have come out with 3 new releases of the name-to-structure tool. So this talk is actually going to focus on the improvements in the name-to-structure tool since June. So we've seen some fairly impressive results. None of these technologies are perfect, but I'll go into that. That title is cringeworthy, I know. But it's meant to allude to the fact that the data that we're dealing with is messy. It's dirty. You see a lot of name-to-structure tools have been around for a while, as most of you no doubt know. And a lot of the benchmarking that was done of them traditionally has been on fairly tame, fairly clean data sets, NCBI lists of chemical compounds, et cetera. And so it's not surprising that you get things like 98% conversion rates. Well, that doesn't happen with patents, as myself and my Steve Boyer can certainly attest to that as well. So without further ado, let's go into the talk. I'm going to try and keep it reasonably short to get us back on schedule, despite my loquacious beginning. Unless this is plugged in. It was working. Oh, there we go. Wrong way. Okay, so I'm going to talk about SureChem a little bit. Some of you may know about it. If you don't, this talk's not really about SureChem. I'm leaving for the airport very soon after this, but if you're interested, come grab a business card, and I'd be happy to send you more information or talk with you about it. I'm going to go over the overall numbers and then look at something called rate of agreement between the tools and then what Chemaxon is bringing to the table that the other tools aren't. So SureChem, briefly, we extract chemical compounds from text and convert them into structures. It's from full text of US, EP, WO patents, Medline, and now Japan patent abstracts. At present, we have a database of 11 million unique structures covering 18 million patent documents, about 19 million Medline abstracts. We have some manually curated data from the USPTO of questionable quality. And we distribute the product via a portal where you can just do searching online, a web service where you can integrate the search with your in-house tools via Pipeline Pilot, et cetera, and then an in-house database product. The workflow, and I point this out. Let's see if I have is this a pointer? Yes, it is. So the workflow, I'm not going to dwell on this, but the documents come in, we pre-process them, we run our entity extraction to get the chemical names out, and the chemical names then go to a pipeline of 3 different name-to-structure conversion tools. Now, I say 3 because traditionally we haven't been using Chemaxon because the tool wasn't around. In future, this number is almost certainly going to change to 4. The names that get converted, they go on to the next step of structure standardization and fingerprinting for substructure search. But a fair number of names will fail due to reasons that I'll point out in a second. And we send them back to an error correction phase, and then they go back through the tool, and the ones that convert will go here, the ones that don't go to a next round of error corrections, et cetera. And then they get published. So we're actually pretty well set up to do some real-world benchmarking because we're using 3 tools. We added Chemaxon for the benchmarking. So we have 4 different tools that we can compare. Name-to-structure challenges, I'm not going to dwell on this because I think a lot of people here are familiar with them, or maybe it's just because I'm talking about it all the time, so it seems old hat to me. But in patents, certainly, for some reason, despite the fact that we've had digital documents for 20 years, patent authorities want you to, with the exception of, it's changing, but traditionally patent authorities have had you take a Word document and print it out and submit it as a printed document, and then they'll scan it, and so that they have a digital copy of it. There are legal reasons for that in terms of the printed image is supposed to be the document of record, but for our purposes, that causes problems like transposed letters and numbers, L's for ones and Y's for V's, etc. Special characters get inserted in plain text. There are some WO patents where you'll see lambda and pi will pop up all the time in the middle of chemical names, and I don't know of any chemical names that should have pi in the middle of them. Names can't be resolved to a structure. So, of course, I mean, people aren't writing these patents so that they can be converted to structures. You'll have inorganic compounds, which none of the tools really handle. Chemical group names, which shouldn't necessarily resolve to a single structure. There's plenty of incorrect nomenclature. I'm just citing a journal article that estimates about 26% of chemical names in literature are unacceptable and can't be converted into structures. That number has definitely got to be higher for patents. Sometimes this is part of it, efforts to intentionally obfuscate, but other times it's just a matter of maybe being a little bit less stringent in terms of forming your nomenclature. And then, of course, the chemical entity extraction process, our process, I mean, it's not perfect, it's software. And so we extract a lot of chemical fragments that shouldn't convert to a structure, and sometimes we'll confuse common words. I mean, an early example was lead, and then we have to use other software to identify context and screen those out. But those are some of the reasons why you're not going to ever get a 100% conversion rate on a patent data set. So we put together a benchmark data set earlier this year. We extracted entities from 900 pharmaceutically relevant patents. These basically were patents that were suggested to us or given to us by customers or while doing custom searches on behalf of customers. And we extracted 100,000 names, 101,000 names, and we converted these to almost 60,000 structures, a conversion rate of 59%, and resulting in 55,000 standard unique smile strings. So using the four tools, we got a combined conversion rate of around close to 60%. If you were to use just one of the tools on its own, or maybe two, you'd be looking more around the 40% range. So, and again, the reason for that is all these various factors about how chemical names appear in patent data. So, what was interesting, and these are the Chemaxon numbers. Now, what I'm showing you is for Chemaxon, the name to structure version 5.2.5, and we were doing 5.2.2 in June. And at that point, and I'll show you the increases in a moment, but Chemaxon did not have the largest number of conversions, but it actually does among the four tools. Now, just because you can convert more than anybody else doesn't mean they're right. So, but the fact that they had that jump is pretty impressive in a short period of time. So basically, all the tools converted around between 35 and then 42% of the names, and then here is the unique structures that were contributed by each tool. Again, Chemaxon has a lot more. That can be both a good thing and a bad thing, but we're very interested in that because if we're adding another tool and we're paying to license it, we want to know what that tool is adding in terms of unique data that the other ones aren't. We also want to look at how often the tools agree with each other and what rate of disagreement there are between all the tools and then on a per tool basis. And I will get into that in just a moment. But these numbers all showed significant improvements in performance from Chemaxon over these three sub-releases. So a little chart. Here, overall conversion went up about almost 17%. So that's the overall number of names converted to structures. Unique conversions rose by 15%. And this is the number that's actually most important. The rate of agreement where all four of the tools will convert the same name to the same structure as defined by by looking at a smile string and doing an exact match analysis on it, went up by almost 20%. That was none of the other tools, all the other tools we were using the same version. That rate of agreement was solely due to the improvements in ChemAxon. And that is significant because that shows, that gives us a way of automatically gauging how accurate our name to structure conversion is, because the only other way to do it is look at it by hand. And you still have to do manual validation as well. But that's a very encouraging sign. So to talk a little bit more about rates of agreement, what we do is we look at how many tools produce a structure where there's only the tool agrees with itself. 2 tools, agreement between 2 tools, or 3 or 4, and then what these numbers. This is the best number up here, is where you have 4 tools that all agree. So you want this number to be higher, and you want this number to be low as possible. Ideally, if you want to have an automated way of gauging the precision of your conversion. And now this is an example. So some of these, in some cases, this is an example of 2 tools that convert the same structure, but to a different, same name rather, but to a different structure. And so in some cases, the differences are really noticeable. In some cases, they're slight. They may be tautomeric differences, et cetera. So just because they differ doesn't necessarily mean it's a bad result, but it's obviously for doing some sort of wholesale automated statistical analysis, this is a fairly useful way of measuring. So we have better rates of agreement. If we're looking at the total benchmark data set of 100,000 names, the 55,000 structures that were produced, compounds with 4-tool agreement are up to 33% from 29%. 3-tool agreement has fallen a little bit, and I think that that's because some of these, the 3 tools shifted over to here. Likewise, the compounds with 1-tool agreement went down, and then with 2 tools, it stayed about the same at 19%. We just finished this benchmarking about a week ago. We haven't had time to delve into the data in great detail, but my past experience leads me to think that the decreases are likely due to the higher 4-way agreement up here. So, also, after this most recent run, there was a decrease in the number of differing structures per tool. That is, if tool number 1, ChemAxon agreed. Well, let's just jump ahead here. So, this shows ChemAxon's rate of agreement with tool number 1. They agreed on 29,000 structures and then disagreed on 3,700. Having these numbers go down is also significant because we're talking about overall rate of agreement, and then looking on a per tool basis, the individual numbers have all fallen. So if I go back, you'll see for the 3 tools, the number of the decrease in the number of names of the same names converted to different structures has dipped from between 12 and 19%. I'm going the wrong way. Pardon me. So in terms of the unique conversions, there were 6,100 unique structures. Again, that's an increase of around 15% from before. Now, this can mean that there are more questionable structures, and I did go through this data. I eyeballed all 6,128 structures, and we have a lot of fragments. Now, that's not necessarily all ChemAxon's fault. I mean, we're the ones who are producing the names, and in some cases, our entity extractor will get tripped up by names in tables, et cetera, and we'll pull out a fragment. What it does suggest, though, is that maybe the ChemAxon name to structure conversion tool may be a little bit too lenient when it comes to fragmenting, or accepting fragmented compounds and converting them as valid structures. But there's also high-value data in there. About 1,800 of these structures appear to be based on years of looking at exemplified structures in patents, are the type of compounds that we refer to as exemplified compounds. That's listed as examples that would fall within the claim of the patent. So, I mean, if out of a set of 55,000 structures, we get nearly 2,000 that are this high quality data, that's great for us. That's a very, very solid contribution and would weigh us heavily towards going and licensing this and making it part of our workflow. Precision estimates. So again, because this benchmarking was just done, we haven't done any hand manual review of the actual somebody looking at a name and then looking at the structure and saying, yes, this conversion is completely valid. We do have the rate of agreement. If all 4 tools agree, and they all have somewhat different approaches into how they convert a name to a structure, you can be pretty sure that those are solid. A manual review that we conducted in late May and early June by Chemaxon, they found that of 200 name structure pairs from the previous benchmarking run, 70% were unambiguously right. There were 20% that were ambiguous or fragments, and then 10% were wrong, either because the names were wrong or the tool generated them incorrectly. I would venture to guess that when we redo this, that we will find that this number is a bit higher, and this number is lower, and this one probably is going to be about the same. If this number of unambiguously correct ones doesn't increase, it'll be because of an increase in the number of converted fragments or ambiguous names. So, but again, based on the improved rate of agreement, I'm expecting an increase in the precision. So the conclusions, in a short time, I mean, this is, everybody else in this field has been working on this for quite some time. So the other tools that we're using, I'm not naming which ones are which in deference to the vendors, but I mean, there's only 3 others. There's CambridgeSoft and ACD Labs and OpenEye. OpenEye is a bit newer, but CambridgeSoft and ACD Labs have been working on this for, I think, maybe, 10 years in some cases. Right. Right, okay, so at least 10 years. So in about a year, Chemaxon has developed a tool that is definitely comparable. It's, as the numbers show today, it's improving rapidly. I mean, we're talking about a period of 2 months. And in terms of integrating it, it's easiest to use. Now, a disclaimer, we are a Java shop, so when you have a Java tool, it's fairly easy. You don't have to write a wrapper or anything to incorporate in the pipeline. But also adjusting the settings on this, it's the most intuitive of the tools to use. And it has a generous range of settings, which is very helpful. I would venture that this tool is here to stay, and we will be licensing it. And with that, I will wrap up my talk. Hopefully I've shaved a little bit of time off of the morning, and if you have any questions, I'd love to take them. Oh, I'm sorry. That was awful. I'm rude. Acknowledgements. My colleagues at SureChem and NetValue, and then, of course, everybody at Chemaxon who contributed. Daniel and Rita did a lot of work on both the validation and making the improvements and supplying us with Gyuri also was very instrumental. Actually, everybody. I mean, Nora helped with the licensing and all that. So a big round of thanks to everyone at Chemaxon, and then my colleagues Richard Litton and Richard Cox and Michael Faust at SureChem. Okay, thank you.
Thank you so much, Nico. Any questions, please? Yes.
I can talk really loud.
Okay.
So, Nico, I think the philosophical question with here, though, is how good do you have to be at this to be useful, right? So, a patent attorney will tell you you have to have everything. Other people will argue. I'm just curious as where you come down. So if you're converting 50% of the structures, is that useful? And if you get from 50 to 70%, how much more useful is that?
Right. Okay. So that depends very much on the patent, the nature of the patent. If this is the overall numbers are a little bit misleading, because if you look at a micro average, if you look at how we're doing within a particular patent, and it's a particularly pharmaceutically relevant patent, it really is a drug. It's patenting a small molecule, and then in that case, the conversion rate for the structures is likely to be higher. Whereas if you get a patent that is more tangentially related, maybe has to do with delivery mechanisms, et cetera, and you also have lots of references to chemical groups and all that, that conversion rate isn't as much of an issue. That being said, I don't think that anybody would ever rely solely on SureChem to issue a complete freedom to operate decision. But the idea is that by casting this wide net, we're able to find structures that aren't found in other databases. I mean, we routinely have our customers find structures that they can't find in CAS, and if only they weren't searching on proprietary compounds, we could have really nice examples on the screen. It's one of the most annoying things I've ever encountered in my whole business career. So the idea is that it's getting you to the right place, and I mean, we want to see that structure conversion rate go up. If it went from 50 to 70%, I actually do think that a lot of people would say, you know what, this is solid enough. But you're always going to have, it really depends on the use case. If you're just doing a general search and you want to find out what patent literature is related, or if you want to see what SureChem has that other databases don't, we're already in a pretty good situation. If you want to say, I need this as the definitive database, I'm not going to look at any other, and by the way, our intellectual property is going to be based, the viability of our IP claim is going to be based on this, then using name-to-structure conversion tools and automated extraction is not, by itself, is not going to do it.
Hi. Just curious, do any of the tools offer any sort of assessment themselves of the quality of the translation that they're making?
What you can do, what some of the vendors have done, is they will take a name, convert it to a structure, and then run a structure to name conversion, those vendors that offer that. And that's more of a check for consistency. But in terms of providing a curated dictionary of terms that you can run validation against, no. Not to my knowledge. I mean, I'm speaking on behalf of the vendors. That having been said, I've actually gotten some of the vendors to give us their internal dictionary. And we've gone through it, and there are problems with some of the terms that are in there. Definitely. The dictionaries themselves have issues. So we're not there yet in terms of a gold standard list. It's one thing that given time, we'd like to work on actually at SureChem, is to publish not only a set of documents for people to run benchmarking on, but also like a gold standard list of names and structures. This is always the hardest question of the session.
No, actually, it's not a question. It was a nice presentation, and thank you. It's just a comment.
Here it comes.
When chemical names do not convert into a chemical structure using a name-to-structure program, often it's because of, for example, a typographical error, a parentheses that's left out, an extra hyphen, it's a colon in the wrong position. It could be a misspelling. It could be a whole number of reasons why, and particularly in OCR data, why a particular chemical name will not convert to a structure. What we found is that you can go back and create rules and say, well, here's a name that went into the program and it did not convert. And then you go into a loop and you say, well, now try to accommodate this broken parentheses or this,
right.
And then go into another loop and put it back in and go into another loop.
That's okay.
And depending on the number of rules that you create, you can get an enhanced performance, even though off the shelf, the program may not be as competitive. So program A versus program B versus program C can have varying performance depending on the nature of the rules that you create,
right.
in using the program.
Just in case this wasn't, I obviously didn't make this clear enough, then we did do that. So we have that little error correction diamond shape is a set of rules for correcting errors, probably not as expansive.
So you use the same rules on every program?
Oh, yeah, absolutely. Oh, it would be unfair to do. Now, there is room for configuring different rules for different tools because of the approaches that they take, but we didn't do that for this because that obviously wouldn't be much of a benchmarking set. We had 3 tiers of error corrections or spelling corrections that we used. So, and after that, we didn't apply anything further. But yeah, absolutely, you have to do that.
Often when you put one set of rules in, a whole number of set of compounds that did not work will,
yes,
or that did work will not work, and so forth.
This is the problem with implementing those rules.
Well, yeah.
Yeah. Any further? Now Daniel will tell you all about the tool. I have to leave for a flight, so we reversed it, and the logic of this presentation order is not ideal. But now you'll find out what it was I was talking about.